Okay, folks, we can get going. It's a little sparse in here. A lot of Super Bowl parties, maybe? I don't know. Before I get, so I'll just remind you that my plan for today and moving forward is to start to get into the Lab 2 content, because folks are going to start wrapping up Lab 1 today, which means, depending when you wrap it up today, you'll probably be starting on Lab 2 today. So it's about time to get into this stuff. Before I do that, though, are there any pending questions about Lab 1? I got one question from, I've gotten a few questions from some students, and it came to my attention that the way that the lab web page is written, there's some ambiguity here. So just to be clear, the sound primitives that you should be able to record and play back, if you're in 4760, should be the swoop, the chirp, and 130 milliseconds of silence. And the reason that we should be able to record back 130 milliseconds of silence is if you look at that spectrogram that we're trying to match at the top, it goes swoop, followed immediately by a chirp, followed by a very brief amount of silence, 130 milliseconds. And so you should be able to record a song that includes swoop, chirp, pause, swoop, chirp, pause, swoop, chirp, pause, and when you play it back, that's what you'll hear. The 5730 students have a few extra sound primitives to also record. Any questions about any of that? I've gotten some questions about looking for advice with regard to sort of application architecture. I'll offer that one design that you might consider for implementing this playback feature, I think one that is, it's not the only way to do this, but one that you might consider, because I think it's, well, it's one of the simpler ways to go about this, is you might consider consolidating playback into its own thread. And so one organization that you might consider, at present, after week 2, you probably have a program that has one thread and an interrupt service routine. And in all likelihood, that thread is doing your keypad scanning and debouncing. So one way that you might consider implementing playback is to retain that and add a little bit of extra state to your keypad thread so that you know whether or not you're in record mode. In the event that you're in record mode, you would log each key press as it occurs to perhaps an array. And we talked last time about how it's perfectly okay for you to statically allocate an array. So you specify the maximum length of the song that a user can record. So if you're in record mode, your keypad thread will know that, and it will record your sequence of presses to an array, perhaps also playing them back as you press them. You might find that to be a nice feature. And then when you switch out of record mode, it could semaphore signal the playback thread, which would emulate the button press associated with the first index of that array so that the sound associated with that button press would come out. Wait until that sound is finished playing and then send the next one, and then send the next one, and then send the next one. A feature of this is that during playback, remember that proto-threads is a non-preemptive threader. So what that means is as long as all threads are on the same processor, which in this lab you're all just using one processor, no thread will interrupt another thread. And so if you organize your program in this way, such that you record your sequence and then signal the playback thread, and if that playback thread retains control of the CPU, that is to say it doesn't yield until it's finished with playback, the consequence will be that the user can't interrupt the song. Just maybe kind of a nice feature. Any other questions about Lab 1 stuff? I'll just mention too, your lab reports for Lab 1 will be due at the beginning of your lab section. You'll turn them in digitally, but the due time is the beginning of your scheduled lab section next week. And you'll turn that stuff in on Canvas. It's one lab report per group, not per person, one per group. And I'll post that assignment on Canvas sometimes this afternoon. Yeah. Oh, good question. So we have break next week. We have off on what, Monday? Monday, Tuesday? So my plan was to say everybody's reports will just be due Friday for next week. Does that seem fair to folks? And then likewise, by the way, for next week's lab checkoffs, because we have a Monday lab section. So the question is, what do we do with the Lab 2 week 1 checkoff for the Monday folks? So for next week's checkoffs as well, my plan was just to say, regardless of which section you happen to be enrolled in, everybody is due on Friday. I don't want to introduce a week of delay at this point in the semester because it eats into our final project time. So this is hopefully a way to allow for people to take a break, and then also we can keep moving along in the class. Yes?
How will checkoffs work next week?
Checkoffs work next week, so you may get your checkoff next week at any point throughout the week. And so come to your scheduled lab section, and if you have lab section, you can do your checkoff during lab as usual, but they won't be considered late unless you do your checkoff after Friday of next week due to the break. Okay, any other lab 1 stuff before I start talking about lab 2? Okay. So let me just remind you then what we're going to be doing in Lab 2. I have a version of it running here. Oops, we have people in the waiting room. Hold on. Let me let them in. I have a version of it running here. So I'll remind you that your task in Lab 2 is a computer graphics flavored lab, and your task will be to make a digital version of a Galton board. That's what you're looking at here. So I'll just remind you that a Galton board is a device composed of an array of pegs organized as shown here, and you drop little balls into the top of this, and they bounce their way down, and then down at the bottom, they get caught in bins that sit beneath this bottom row of pegs. The bins aren't pictured here, but what we are picturing is a normalized histogram that shows the number of balls that have fallen into each bin below this Galton board. You've probably seen gamified versions of this thing on like The Price is Right and some other game shows, and if you go to some fairs and so forth, there's often a game associated with this that they give different names. But in its original formulation, it's called the Galton board, named after Sir Francis Galton, who invented it. The objective here, this is an optimization lab, so you will be challenged to animate as many balls falling through your Galton board at 30 frames per second as you can manage. And so in order to get the most balls going through your Galton board that you can manage, you'll have to optimize your code. So the group that gets the most balls will be the one that is most thoughtful about how they organize their code and most obsessive about how they optimize it. So some of those optimizations will include fixed point arithmetic, like we talked about last time. That was sort of a optional for fun thing in Lab 1. In Lab 2, you're going to have to use fixed point arithmetic, because if you use floating point, you just won't get very many balls going through your Galton board. And then we'll talk about a few other techniques as well. And then, because this is interesting, you'll be asked to do things like visualize this histogram and implement a user interface that's actually a little bit different than the one I'm demoing here. The user interface that I've been showing off in class is a serial terminal one. You'll be asked to build a user interface based on a button and a potentiometer. So it sort of makes the thing a device. So this is the goal, and I thought that perhaps a nice way to introduce this lab would be to remind you of some of the interesting statistical concepts that this is just demonstrating. So these devices, they're really interesting because they include 5 really fundamental statistical concepts. They include Bernoulli trials. I'll just remind you that a Bernoulli trial is a random experiment with 2 possible outcomes. So a coin flip would be an example, though it needn't be a fair coin. It could be a weighted coin as well, but just some experiment with 2 possible outcomes. So every time it hits a peg and it can go left or right, that's a Bernoulli trial. It includes, after all these Bernoulli trials, what you end up at the bottom is a binomial distribution, which you may remember from some statistics class at some point. As the number of rows increases here by the central limit theorem, yet another core statistical concept, that binomial distribution will start to approach a Gaussian distribution. And that's some of the math that I want to remind you of in the lecture today. And then this whole physical system incorporates Pascal's triangle in a really delightful way. So I want to remind you what Pascal's triangle is and show how it relates to this system. So I thought we'd spend maybe, 15, 20 minutes just reminding you of some of the interesting math that this is demonstrating, and then we'll get into some of the code. Any thoughts from anyone before I do that? You can buy little desktop versions of these, by the way, on Amazon for like $10, and they're really cool. Okay, so then let me remind you of some of this, the interesting statistics that this incorporates. So in order to have this conversation, I thought we'd introduce just a little bit of notation. So the way that we will be talking about these Galton boards for purposes of this discussion is we will imagine that the little bins underneath the Galton board in which the balls fall, we're going to label them 0 through, as many bins as there are, 0 all the way on the left. And we will imagine that our ball drops into the middle of this board, which will always be located at a position that's equal to the total number of bins under the Galton board divided by 2. So in this case, that ball is falling at position 2.5. And every time the ball strikes a peg, it will, in an idealized Galton board, with a 50% probability, it'll either bounce right and increase its position by 1/2 units, or it will bounce left and decrease its position by -1/2 units. And it'll bounce, 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 and land in one of these at the bottom. Our choice to increase and decrease position by 1/2 or -1/2 is just a matter of convenience, because it means that when you sum all these up, you end up with these nice integer numbers at the bottom. Okay? So that's what the Galton board is. And what we're interested in having a conversation about and thinking about is, as we increase the number of rows in this board, what distribution do we form down here? And the way to start investigating something like that is with, as always, you start with the simplest conceivable version of whatever system it is that you're trying to understand. The simplest conceivable version of this system would be a Galton board with 1 row in it. Which isn't much of a Galton board, it's a peg on which balls bounce. Okay, but let's start with that. So for a 1-row Galton board, what we have is a Bernoulli trial. We have a random experiment with 2 possible outcomes, bounce left or bounce right. In an idealized Galton board, those probabilities are 50% left, 50% right. And we can generate the distribution here of balls in bins, essentially, for a 1-row Galton board. And what you end up with is the very predictable and very boring distribution shown here. As you would expect, if you bounce a ball off of 1 peg, it's going to, with 50% probability, go here or here. And so you end up with 50% of your balls on the left in bin 0, 50% on the right in bin 1. We should actually, let me see. If I change our number of rows to 0, here is this animated. So I've dropped the number of rows in our Galton board to just 1 row, and what you can see is our distribution at the bottom here goes 50% there, 50% there. Okay. So we sort of knew that that would happen, but that's where you start. And then the next thing that we'll do is start building up rows of this Galton board. The general strategy here is you start with, yes?
I'm a little confused. If the peg is in a stationary position, if we drop all the balls the same way, wouldn't they all bounce the same way?
Yeah, so the assumption is that, it's a good question. The assumption is that the initial conditions of the ball are a little bit randomized every time. And so you aren't dropping it on the same spot on the peg every time, because you're absolutely right. It would just be deterministic. You're sort of randomizing it a little bit so that it has 50% chance of going either direction. Yeah?
Actually, next to what I was going to ask, are we introducing like randomness for the lab, or are we like seeding it?
You are. So you'll, as we'll talk about in a moment, each ball's state will include its position, x and y, and its velocity, vx and vy. And you will be encouraged to use fixed point to represent all of that state. You'll use some of those techniques we talked about last time for generating random numbers in fixed point in order to randomize your x velocity a little bit, so that it might bounce this way or that way off that first peg. Any other questions about this? Okay, so let's add 1 more row. And I'll just, I'll mention that the strategy that we're deploying here is we're starting with 1 row, seeing what we end up with, adding another row, see what we end up with, add another row, see what we end up with, under the hypothesis that perhaps we'll recognize a pattern. And in the event that we recognize a pattern, we could then try to prove that that pattern holds for n numbers of rows, and then we will have sort of solved this system. So let's now add a 2nd row. So what we have now is not a single Bernoulli trial, but we have instead the sum of 2 Bernoulli trials, x1 and x2. So we bounce off the first peg, we might go this way or this way. After having bounced, we'll land on the next row of pegs, we might go this way, we might go this way. And then I have an offset here of mu just to represent the non-random number, which is where we dropped this thing to begin with, right? So the random numbers are each choice, and then there's a non-random number, which is where we start. So the possible values that our random variable y here, our random variable y is the bin in which our ball lands, that can assume 3 possible values, according to the convention that we're using to label bins up here, right? For a 3-row Galton board, I'm sorry, for a 2-row Galton board, which you could imagine as just being sort of this lower left corner, you're either going to land in bin 0 or bin 1 or bin 2. And the question is, what's the probability of landing in each of those bins? And the way to answer that question is to compute. We can compute each of these probabilities separately for a Galton board as small as this. So let's compute the probability that we land in bin 0, that random variable y is 0. The way to go about this is to sum over all possible values of one of the random numbers. And once we consider all the possible values of the first random number and ask, what would the other random number's value have to be in order to give us the outcome that we're interested in investigating here? So for example, let's suppose we're computing the probability of landing in bin 0. Well, that's the same as asking, what's the probability that x1, our first Bernoulli trial, and plus x2 is equal to -1? Right? What's the probability that we bounce left 2 times? And we could rewrite this. That probability, the sum of those two, that sum being 1, is the same as the probability that x1 is -1/2, we bounce left, and x2 is -1/2, we bounce left again, plus the probability of another situation that would land us in that bin, which is the probability that x is +1/2, we bounce to the right, and x2 assumes the impossible value of -3/2, right? That's the only way that we could get back to 0. Now that's an impossible value because we can only move by 1/2 per bounce, right? So as we'll see, that probability ends up being 0, but we're considering all possible outcomes, we're considering all conceivable outcomes, even the impossible ones. Because each of these random numbers is independent, the probability of that and that is equal to the product of their 2 independent probabilities. And so we say, well, the probability that x1 is -1/2 and x2 is -1/2 is the product of x1 being -1/2 and x2 being -1/2. And then likewise over here, we know the probability of each of these events. In order to keep this derivation general, I'm saying that the probability of bouncing to the left is, or to bouncing to the right is p, bouncing to the left is 1 minus p. In an idealized Galton board, p is 1/2, right? But just to keep this general, we'll keep it like this. And so the probability of x1 bouncing to the left is 1 minus p, of x2 also bouncing to the left is 1 minus p. So that's our left term of the expression here. The probability of x1 bouncing to the right is p, and of x2 bouncing to the left by -3/2 is 0. So that term goes away. And what we find out is that the probability of landing in bin 0 is 1 minus p squared. In the event that p is 1/2, we have a perfect Galton board, then that would be 0.5 squared, 0.25. Okay, what about the probability of landing in bin 1? Well, by a nearly identical analysis here, right? If we're landing in the middle bin, how might have we ended up in the middle bin? We could end up in the middle bin by bouncing left then right, or by bouncing right then left. Those are the 2 options. And so we can compute the probability of each of those using exactly the same sort of analysis that we just did, though in this case, there's no situation in which that second variable x2 has to assume an impossible value, right? So both of these remain valid. And we end up by the identical analysis really with a probability of 2p times 1 minus p. In the event that p is 1/2, that would be 2 times 1/2 would be 1 times 1 minus p, 1/2, so that would be 1/2. So we end up with 0.25, 0.5, and perhaps predictably, the probability of landing in bin 2, the other side is the same as landing in bin 0, right? We end up with p squared here. And so if you were to plot this, you end up with the following, right? It's a simple distribution, but we're building our way up. And let's see, if I change our number of rows here to 1, you can kind of see that distribution starting to take shape here. Now, by the way, this whole analysis, the mathematical analysis that we're going through, is for an idealized Galton board. An idealized Galton board is one where the ball hits a peg in every row, and every time it hits a peg, it has a 50% chance of bouncing this way or this way. You're making a physical simulation of a Galton board, which isn't idealized, but for reasons that we'll talk about, you end up also approaching a Gaussian. Okay, so then I won't necessarily go through every step of the next one, but we can continue this process. So we've got one, we've figured out a 1-row Galton board, we figured out a 2-row Galton board. You could figure out a 3-row Galton board where you ask what's the probability of landing in bins, 0, 1, 2, or 3. And by going through the same exercise that we just illustrated, you end up with your probabilities down here, and you end up with a distribution that looks like this. We could walk through this if folks like, but it's exactly the same kind of analysis that we just saw. You're considering every possible value for one of your random variables and asking what value must the other random variable have assumed in order to give us the bin number that we're asking for. Okay? And at this point, after having gone through 3 rows, we can in fact start to recognize a pattern if we look carefully. And the pattern that we would start to recognize is that the probability of landing in bin K from the left, the probability of landing in bin K, is given by the binomial distribution. So that's, n choose k, p to the k, 1 minus p to the n minus k. And we could, and the associated reading for this lab, in fact, does prove by induction that that is indeed the case. So we've gone through 0, 1, and 2, 1 row, 2 row, 3 row Galton boards, identified a pattern. The pattern that we noticed is that, boy, these probabilities seem to be assuming a binomial distribution. And then we could prove by induction that that pattern holds for an n-row Galton board. I won't go through that proof by induction here, but it's in the reading if you'd like to take a look at it. And that more general equation simplifies in the case of an idealized Galton board, where p is just 0.5, to what's shown here. N choose k times 1 over 2 to the n. And so this little animation shows us, as we increase the row of the number of rows in our Galton board, what does the distribution of balls in pegs at the bottom look like? So for a 1-row Galton board, as we just sort of went through, you expect to find 50% in 0 and 50% in 1, of course. For a, how do I step forward by 1? For a 2-row Galton board, which we also investigated, you expect to see 0.25, 0.5, 0.25. For a 3-row Galton board, oops, spoiled it. For a 3-row Galton board, you expect to see what we looked at but did not explicitly derive in the same way as the first two shown here. And as we increase the number of rows, here's what our distribution does. All right, so let's go up to, say, 50-row Galton board. Remember, for a 50-row Galton board, we're dropping the ball at position 25, right in the middle. And what you see is that most of the balls land at position 25, but then they form this nice distribution, which might start to look like an old friend to you, right? It starts to look awfully Gaussian. But notice that that Gaussian appearance, it becomes more and more Gaussian looking the more rows that we add, right? So I want to do just a brief aside here. Folks remember Pascal's triangle? Where is Pascal's triangle introduced? It's in high school at some point. In what context do you learn about this? Can't remember. Do you remember? Yeah, it's useful for that, right? It turns out it has a whole bunch of different uses. One of them is expanding quadratic equations. It organizes the binomial coefficients. So the coefficients of this binomial distribution up here, right? It organizes these. Has a bunch of kind of other interesting properties that I won't necessarily get into, but in the context of this conversation, what it ends up representing is the number of paths that a ball could take to a specific location. Okay, so for instance, we have a 1, 2, 3, 4, 5 row Galton board here, and here are all the bins beneath the Galton board. And the numbers here are the numbers that come from Pascal's triangle. So we have 1, 1, 1 at the top, right? We have, 1 plus 1 is 2 here, 2 plus 1 is 3. You may remember how you build up, the Pascal's triangle by adding the 2 above it. So you build this up. What you end up down here is 1, 4 plus 1 is 5, 6 plus 4 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and 1. And in the context of this idealized Galton board, what these numbers represent is the number of paths that you could take to get to that spot. And so this 5 here, for instance, what are the paths that we could take to get here? Where we could bounce left, 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 right. That's 1. We could bounce left, 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 right, left, 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 right, left, left, and so on. If you add all those up, there's 5 possible paths by which you could bounce your way to that spot. There's 10 possible paths by which you could bounce your way to that spot. There's 1 possible path by which you could bounce your way to this spot. You have to bounce right every time in order to get all the way to the outside. And so every one of those paths has an equal probability of occurring, right? Every path is described by a series of left-right decisions. And so, you have a 1/2 chance of going that way, 1/2 chance of going this way. The chance of getting to any position down here would be 1/2 to the n. That is, in fact, this term up here. It's 1/2 to the n. That describes the probability of any particular path. So this is the probability of any particular path. And this here, this n choose k, represented on Pascal's triangle, represents the number of paths that get you to that spot. So 1/2 to the n, that's a probability of any path, times, in this case, 5. That's the number of paths that get you here. Just kind of a delightful physical interpretation, right? Okay, but that's just a little aside. So you will have noticed that as we increase the number of rows, that distribution starts to look more and more Gaussian. And in fact, it's becoming a better and better approximation to a Gaussian. That binomial distribution described by those binomial coefficients starts to approach a Gaussian. The reason for that is what you're observing is the central limit theorem. So what you may recall is what the central limit theorem states is that when you sum up a bunch of independent, identically distributed random numbers, with a couple of other slightly more subtle caveats, they have to have finite variance. We do, okay? But identically distributed, independent random numbers from any old distribution, as long as it's finite, right? Any distribution you want, you add those up, and that sum approaches a Gaussian. You can normalize that too if you want. Another way of an essentially equivalent statement is to say that the average of a whole bunch of identically distributed independent random numbers approaches a Gaussian. So that's what we're observing. So as the size of our Galton board increases, the binomial, which describes the ball distribution, approaches a Gaussian. This is the general equation of a Gaussian. You may remember that all that you need to know in order to write down the probability density function for a Gaussian is its mean and its variance, right? You need to know its mean mu, and you need to know its variance sigma, and that fully specifies the Gaussian. So the question is, for our Galton board of n rows, some number n rows, how do you compute those two numbers? It turns out it's really not so hard. So in order to compute the mean and the variance of the n row Galton board, the mean and variance of the Gaussian, which approximates the binomial that describes the bin distribution, we can arrive at this by thinking about the expected value and the variance of each independent little trial. And then because all of these are identically distributed, the mean and the variance of the sum of them, it's just the sum of each of these, right? And for these Bernoulli trials, this is really easy to think about. So let's think about the expected value of one of these Bernoulli trials, boink or boink. The way that we compute an expected value is for every possible value of that random value, we multiply the probability of it achieving that value by the value itself, and then we add up all of those, right? So in the case of a Bernoulli trial, we have a 50% chance of moving left by 1/2, a 50% chance of moving right by 1/2. So you add all this up and you end up with an expected value at the result after doing this trial of 0, which is maybe matches your intuition. You can think about this expected value sort of as the center of mass of the resulting distribution. And for that 50% here, 50% here distribution, the center of mass of that is right in the middle, right? And so we should expect to find the expected value right there in the middle at 0. That's where we find it. And by a nearly identical analysis, we can also compute the variance of a single Bernoulli trial. I'll remind you that the variance is the expected value of a slightly different random number. It's the expected value of the random number in question, in our case x1, boink or boink, left or right, minus the expected value of that squared. We just computed the expected value of that and found it to be 0. So as it turns out, the variance of x1 is just x1 minus 0 squared, or the expected value of x1 squared. And so in order to compute this, all we have to do is take each possible value of x1, square it, multiply it by the probability of x1 assuming that value, and add them all up. So that would be 0.5 times minus 1 squared plus 0.5 times minus 1/2 squared plus 0.5 times 1/2 squared. And we end up with a variance of 1/4. So the expected value of a Bernoulli trial is 0. The variance of that trial is 1/4. And then all that our Galton Board is the sum of a whole bunch of these identically distributed, independent, random Bernoulli trials. So because these are all independent, the following holds. The mean of the sum is equal to n, the number of trials, times the mean of each trial. The expected value of each trial, which we just found was 0. We're going to offset this by where we actually drop it, right? And then the variance is n, the number of rows, times the variance of each trial, which would be n times 1/4, or n over 4. We're going to offset that 0 mean by the non-random position where we plunk it into the table, right? So what that means is the expected value of the distribution at the bottom of our Galton board is given by n over 2, which we kind of saw empirically, right? When we were looking at this, we noticed that, you could notice that the expected value of a distribution is its center of mass. Center of mass sure looks like it's, boom, right in the middle, and indeed we found that it is, right in the middle there. The variance of an n-row Galton board distribution is going to be n, the number of rows, over 4. Which means that the standard deviation, which is just the square root of the variance, is root n over 4. And remember, all that we need in order to fully specify a Gaussian is its mean and its standard deviation. So now we can just take those two numbers, which are a function of the number of rows of the Galton board, and plug it in. And here is our expression for the Gaussian, which approximates the binomial that's forming at the bottom of our Galton board. And we should expect that this approximation gets better and better and better as the number of rows increases. So just how good is it? Well, for a one-row Galton board, it sucks, right? Here's the Gaussian, and here's our actual binomial distribution, and it's not a very good approximation. As the number of rows in our Galton board increases, it does a better and better job approximating that binomial distribution. And honestly, after what is to me if I didn't know anything about this and you asked me to guess how many rows does it take before you get a pretty darn good approximation, I would have guessed way more than it actually takes. It starts to do a really nice job approximating this after what is to me a counterintuitively small number of rows. After as few as 16 rows, which is as many as yours will include, the Gaussian distribution is pretty darn good, right? Now what's powerful about this is once you have a Gaussian, it's so darn easy to do analysis. And so it allows for us to answer questions that at first blush seem like they would be so complicated to answer, but because of the central limit theorem, which allows for us to approximate these distributions as Gaussians, we can arrive at the answers to otherwise extremely complicated questions extremely quickly. Let me give you an example. Let's suppose you have a behemoth of a Galton board, 1,600 rows, a huge Galton board. What is the range of bins that will catch 68% of the balls? Now, if you didn't know about the central limit theorem, that strikes me as almost an impossibly complex question to try to answer, right? But because of the central limit theorem, this becomes really rather simple. Now, I've chosen 68% here because it's especially easy. You may remember that 68% of events is within one standard deviation of a Gaussian, right? So it makes this especially easy, okay? So 68% of our drop balls fall within one standard deviation of the mean. And so we just came up with two equations that are functions of the number of rows that allow for us to compute the mean and the standard deviation of this approximating Gaussian. And so in the case of a 1,600 row Galton board, the standard deviation is going to be root n over 4, root 1,600 over 4, which is 20. And so 68% of our balls are going to land within 20 positions of our mean, which is right in the middle, right? And so that means, I lost my position here. So you get the point. We know where the middle of this distribution is. We've just very quickly been able to figure out what one standard deviation is. So now we just know that 68% of the balls are going to land within bins 980 to 1020. We did that with an amount of arithmetic that probably most of you could do in your head. And so it reduces an otherwise phenomenally complex problem to one that is almost mental math. Yes?
Why is the sensor at 1,000 instead of 800?
Because I messed up. That's a typo. You're absolutely right. The mean of this should be at 800, not at 1,000. Good eye. So it's an incredibly powerful thing to know about. I will just caution you, make sure if you're about to apply central limit theorem thinking that the conditions under which the central limit theorem hold do in fact hold. Make sure, for instance, that the system that you're thinking about includes the sum of a bunch of identically distributed, independent random variables with finite variance. But it's good to know about. Okay. Any questions about this stuff before I move on? So I mentioned on the first day of class, these labs are what they are for a bunch of reasons, one of them being I find them interesting. I talked to you about why I find the bird song so interesting. This summarizes why this is so interesting. Have people seen this statistics stuff before? Yeah, okay, I thought so. I hoped so. All right, so then, let's just take a look at the code, and then we'll spend a considerable amount of time next week going through it. And in fact, before I even pull up the code, let's pull up the lab write-up. So what you'll be asked to do in week 1 of this lab is make a 1-row Galton board, a peg and a ball, bounce the ball off the peg, and every time the ball hits the peg, there should be a thunk sound, thunk. And so that's going to involve the integration of 2 demos. One of the demos is an animation demo that just shows 2 balls moving around the screen. And the other one is a direct memory access demo that produces a pure sine wave, not using direct digital synthesis, but instead by just shuffling data off to the speakers through DMA channels. You'll integrate these 2. And so we could really talk about these 2 demos in either order. I think I'm going to start with the animation one and then talk about the DMA one. DMA one opens up a longer conversation. And every one of these collisions is not going to be, you are not going to be implementing an idealized Galton board where the ball strikes and you flip a coin and go this way or this way with 50% probability. You're going to be actually modeling collision physics between 2 balls. So that makes this not an idealized Galton board because how you bounce off of this ball does in fact affect the range of possible bounces off of this ball, right? So each of these trials is not identically distributed. As it turns out, it still approaches a Gaussian because this is the verbiage here is this is a mixing process. One way to think about this is that though the direction that you bounce off of this ball depends perhaps a lot on the way that you bounce off of that ball. As you move down the rows, your ball basically forgets about previous bounces. The effect of this bounce is negligible by the time you get down here, perhaps. And so it ends up behaving in a similar way, because considered over sort of like chunks of rows, it is in fact essentially identically distributed, just not from row to row to row. So some of the concepts that this is going to introduce, like I said, fixed point, animation concepts. We're going to review some collision physics. We're going to talk about DMA for sound production. The challenge here is as many balls as you can. And so unlike lab 1, where you're doing audio synthesis in an interrupt service routine 50,000 times a second, you don't want the CPU to ever leave your animation loop unnecessarily. You don't want to be taking those interrupts that take away from your animation time. So we're going to offload all sound production to direct memory access channels. We're going to talk about the analog to digital converter, because your interface to this tool is going to be a button and a knob, a potentiometer that allows for you to smoothly adjust parameter values. So there's a lot of good stuff here. Let's see. So let's just take a look at the animation code. And I think all we're going to probably have time for today is to look at the structure of it. And then next time we'll start going through the details. So structurally, actually, let me see if I can program this up so I can show you what it's doing. Let us see. Did that work? Let's see. Looks like maybe no. Oh yeah, there it is. So here's the animation demo. I'm using a VGA capture card here, so you'll see this. Oops, disappeared. Where'd it go? You'll see this on the VGA screen. Oh, maybe not. Hang on, hang on. Well, that's okay. Never mind. You got a glimpse of it. All that the animation demo is doing is bouncing 2 balls around a little arena. And one of those balls is being animated on core 0. The other of those balls is being animated on core 1. So the other new concept that's going to get introduced this lab is multi-core programming. So structurally, let's take a look at what this program looks like. And then, of course, we'll spend a lot of time going through it. As before, we have a bunch of our includes at the top. Some new ones this lab will include the VGA graphics library, because we're going to be driving the VGA screen. Everything else is largely the same. A couple new hardware interface libraries, DMA here, PIO here for driving the VGA screen. Clocks and PLL, because you're probably going to want to overclock to get the most balls that you can. Beneath those includes, we have a bunch of macros, including those fixed point macros, which I alluded to last time in lab 1, and that in lab 2 you're going to absolutely want to make use of. So here's a bunch of, we type define our fixed point variable up there, fix 15, and then here's our multiply routines, our type conversion routines, etc. A couple of macros for quickly checking threshold values. Our frame rate in microseconds. I'm enforcing 30 frames a second. And then this particular demo only animates 2 balls. The variable name Boyd here is an artifact from a previous version of this lab, was the Boyd's algorithm, and I forgot to swap ball for Boyd, so Boyds are balls. In any case, there's 2 balls here, each of which has position state and velocity state. So there's x and y position, vx and vy velocity for 2 separate balls, and all of that state is being maintained as a fixed point value. A couple of helper functions, one of which spawns a new ball at the top of the screen. Another which draws the little rectangle that you may have caught a glimpse of. And then another one that checks the position of the ball each frame, and in the event that it has struck a wall, it reverses its velocity in the appropriate direction to implement an elastic collision with the wall. So some helper functions, and then what I really wanted to show you here is we have 3 threads in this example. One of them is this proto thread serial thread running on core 0. This is implementing that non-blocking print and scanf that I alluded to in a previous lecture. We're going to spend a considerable amount of time talking about this, but I'm just pointing out that this is allowing for us to print information out, things like input a number in the range of 1 to 15, without blocking. So what this will do is send that first character I off to the UART peripheral and yield the thread so that your animation thread can continue to run. Once that thread's been printed, this thread will run again to print the next character, again in a non-blocking fashion. So this is addressing that issue we talked about last time where printf takes up so much time. This is, we're yielding between every character so that our animation thread can continue to run. And then likewise, this serial read allows for us to prompt for user input, but not block on that user input, in contrast to something like a scanf, which would stall. So we have a thread here that's asking for user input. In this case, all that it's asking for is a number in the range of 1 to 15, and it takes that number and changes the color of the balls based on the number. And then we have 2 animation threads, one on each core. And we'll talk about this in more detail in the coming lecture, but let me just show you generally how it looks. As always, the thread begins with a PT begin, ends with a PT end. In this case, we have 2 static local variables, begin time and spare time. Before entering our while one loop, we spawn a ball here. That is to say, we just give that ball an initial set of conditions. And then the animation loop looks like the following. Every time we get scheduled, we check the current time on the microsecond timer. We erase the ball, which is the same as drawing a black ball over the present position of the ball, right? We want to, in order to spend as little time in this thread as possible, we only want to affect exactly the pixels that we need to change. So we don't black out the whole screen. We just draw over the ball that we want to erase. We compute that ball's new position and velocity by way of this function. So this updates the x and y position of that ball, updates the x and y velocity of that ball. We redraw it. This redraws that rectangle. And then we ask, how much time do we have left? In other words, for a desired frame rate, for us it's 30 frames per second, we check the current time of the microsecond timer after having done all this stuff and subtract off the time that we measured before having done this stuff. In other words, how much time did we spend in the thread? And we subtract the amount of time that we spent in the thread from our desired frame rate so that we yield for precisely the amount of time that we need to in order to have this thread rescheduled 1/30th of a second later. So we want for this thread to run 30 times a second. If you have very few balls in your Galton board, it's certainly the case that your animation thread will finish early. You have to yield it for the appropriate amount of time before it runs again to enforce a 30 frame per second frame rate. If you don't do that, your balls will just fly around. Basically, as you decrease the number of balls, you'll find that they move faster and faster and faster because your effective frame rate's increasing. We want to hold the frame rate constant, and this is how we do that. So we measure the amount of time that we have left, and then we yield for that amount of time. So your challenge will be to cram as much ball update in there as you can while keeping spare time positive. There's an identical animation thread on the other core. The only difference here is that it is looking at that other set of variables, tracking the state of the other ball, but it is identical. And then the last thing that I'll just point to here is how do you actually deploy this second core? We'll talk about this in more detail, but let me just give you a teaser because it's alarmingly easy. If we want to launch code on the other core, we can reset it by way of a CSDK function, and then we can launch core 1 by way of a CSDK function. The only argument that this takes is a pointer to the function that we want to use as main on that other core. So we're pointing it to this function, core1 main. Note, all main on the other core is doing is adding a thread to the scheduler and starting the scheduler. And you may recall that ProtoThreads here is smart enough that it knows I'm on core 1, the other one knows it's on core 0, and so any threads that you add to core 1 will run wholly independently from threads that you put on core 0. And so all these threads are created the same. When we create the threads, we don't have to tell the thread it's on core 0 or core 1. But just by adding it to one core or to another core, we put that thread on one or the other core. So you'll probably have an animation thread on each loop, and then you'll probably have some other user interaction thread on, you have an animation thread on each core, and then a user interaction thread on one of the two cores. So much more to come. Yes?
When you do pass a negative value into yield, does it throw an error or does it not?
Does not throw an error. I think, I have to double check this, but I think that I think that yield here is looking for an unsigned int. In the event that you pass a negative number, I think it'll interpret that as a huge number and just freeze. I hope it does that because that's very easy to spot. Okay, I will be in lab this afternoon. I'll see some of you this afternoon. I'll see the rest of you Wednesday.